Hello everyone, today we will see about the solution of second order linear recurrence relation with constant coefficient. So from the definition, a linear degree k homogeneous recurrence relation with constant coefficient is represented by or defined by this one, order k, c1, c2, ck are constants. So it's a homogeneous recurrence relation with constant coefficients. And it's linear because there is no power or product of the numeric terms of the recurrence relation. From this definition, we can take a second order linear recurrence relation is represented by this one. Second order linear recurrence relation is represented by this one, or you can represent this one by splitting the nth term and expressing it by the previous terms of the sequence, where C1 and C2 are constants. Now, to find the solution to this recurrence relation, we can start from the initial guess as a solution to this recurrence relation to be this term, Then substituting this sequence on the recurrence relation, you will obtain this one r to the power of n when you are substituting on the an term, then plus c1 r to the power of n minus 1 and plus c2 r to the power of n minus 2, which is equal to 0, subsequently substituting on n minus 1 and n minus 2 terms. Now taking the common term on this equation, which is r to the power of n minus 2, then we get this equation. R to the power of n minus 2 times r squared, which is what's left on this one, the remaining part from r to the power of n, when we are taking r to the power of n minus 2 as common, which is r squared plus c1 r plus c2. Now, you can see that by dividing r to the power of n minus 2 on both sides, you'll get that r squared plus c1 times r plus c2 is left, and this equation is said to be the characteristic equation or the characteristic polynomial to the recurrence relation. And clearly you can see that it is a quadratic function, and the roots of this quadratic function may be are 2, and these two roots may be identical, or they may be distinct, or they may be complex conjugates. Now, in this section, we will see the second case of the roots of the characteristic equation when there are two equal roots, when the characteristic polynomial or characteristic equation has two polynomial roots alpha. Then the general solution to the recurrence relation will be this one, which is an is equal to p times alpha to the power of n plus q times n. N is due to the repeated root of n times alpha to the power of n, will be the general solution, Let's see with an example. Solve the recurrence relation defined by n is equal to 4 times n minus 1 minus 4n minus 2 with initial conditions n is equal to 1 and a1 is equal to 1. Now, the characteristic equation to the recurrence relation, this recurrence relation is x squared plus 4x plus 4, which is minus, it's just to say minus 4x plus 4. Then what are the numbers where their sum is minus 4 and their product is positive 4? The numbers are minus 2, where the numbers are minus 2, minus 2. So x minus, sorry, this one, so x minus 2, the whole square, which is equal to 0. So which is a perfect square. So the root is x is equal to 2 with multiplicity 2. The root 2 is 2 times the roots of the characteristic equation. So the solution to the recurrence relation, the general solution to the recurrence relation, is given by an is equal to p times 2 to the power of n plus q times n times 2 to the power of n. N is added due to the repetition of the roots 2 times. Now, in order to determine the coefficients p and q, we can substitute the initial conditions which is given or associated with the equation, the recurrence relation. So when n is equal to 0, substituting n is equal to 0, you'll get a naught. A naught is clearly 1. 1 is equal to a naught to the power of 0 plus q times 0, which is 0. When you're substituting 0, this term becomes 0. So 1 is equal to n is equal to p. So the p value is 1. And when we substitute n is equal to 1, we get a1, and a1 is minus 1. So 2 times p plus 2 times q, but p is clearly, we obtain that p is 1. So q is rearranging the value, you'll get the q value, which is minus 1 over 2. Hence, the particular solution to the recurrence relation is given by this equation, which is n is equal to the power of n minus n over 2 times to the power of n, and taking to the power of n as common to the power of n, which is 1 minus n over 2 is a particular solution to the given recurrence relation. Let's take another example. Solve the recurrence relation. Solve the recurrence relation. N is equal to 6 times n minus 1 minus 9 times n minus 2 is initial conditions. Mostly initial conditions are given with the question to find the particular solution of the recurrence relation. So before finding the particular solution, we are going to determine the general solution. Then from the general solution, substituting these initial conditions, we give the particular solution. So the characteristic equation to this second order linear homogeneous recurrence relation is given by r squared minus 6r plus 9, which is equal to 0. And the roots of this quadratic equation is obtained by finding the two numbers where their sum is minus 6 and their product is 9. So the numbers are minus 3 and minus 3. Their sum is minus 6 and their product is positive 9. So r squared minus 3 the whole square, r minus 3 the whole square, which is equal to 0. So r is equal to 3 is the root of the characteristic equation with multiplicity 2. With multiplicity, these two, multiplicity is just number of repetition, the number of how many times the root of the equation is repeated. It's just said to be the multiplicity of the root. So the solution to the recurrence relation is, since the root of the characteristic root of the roots of the characteristic polynomial or the characteristic equation are repeated, so we can use that one, so that the general solution to the recurrence relation is given by this one. A n is equal to p times 3 to the power of n plus q times n minus 3 to the power of n. Let's now determine the values of the constants so that we can get the particular solution. So substituting n is equal to for n is equal to 0, we get 2, which is equal to n naught is equal to p, because when we are substituting n is equal to 0 here, it makes the whole 0 value, so that p value is 2. We get 2, p value 2. Then substituting n is equal to 1 on this one, it becomes 5, which is equal to a1 is equal to 3 times p plus 3 times q. Then q, substituting the p value, which is 2, on the equation, we get q is equal to 1 over 3. Q, which is equal to 1 over 3. Hence, the particular solution to the recurrence relation. The particular solution to the recurrence relation is given by this one. Now we will see on the next section about the case 3, which where the roots of the characteristic equation becomes complex conjugates of the recurrence relation.